you to cast your mind back and think about how you actually solved the problem. So what was your strategy? Essentially, what algorithm did you use? Did you pick the shortest paths every time? How did you choose where to start? What features of the problem were important? So I'd like you to just pause the movie again, go back and have a think, and try to jot down a rough description of the method that you used to solve the problem. So the next question to ask ourselves is, how can we take this problem and simplify it such that we can represent it in such a way that it could be solved by a computer? That is, how do we take this diagram and convert it into a data structure that we can analyze using an algorithm that we've translated into a program? Remember, this is what we call the process of analysis. Okay, simplification and boiling down a problem to its core components. And this is basically the Marie Kondo approach to analysis. In order to find out what we need, we get rid of what we don't need. So let's look at this diagram and find out what we can get rid of at no cost to our understanding of the problem. Okay, so fundamentally what I'm asking is, what's the important information in this description of the problem? What is relevant and what is irrelevant or otherwise unnecessary? Fundamentally, what is the minimum information we need in order to solve the problem? What are the key words? So what I want you to do now is pause the movie, have a think, and maybe circle or make a note of only the key information that we need to solve this problem. When you think you have it, come back. So thinking about it, this is all we really need to know, and I've circled the important information here in red. We don't need to know about the birds or the kid on the bike or that one of the houses is for sale. We don't even really need to know that we're dealing with something called a town or that we're the mayor. We just need to know that there are things called houses, our nodes, that are connected by paths, that is the links, and that each path has a length. And then the problem is just, how do we find a set of paths that keeps the houses connected using the smallest number of blocks? So it's houses, paths, smallest number of blocks, and the fact that each link has a length. That's all we need to know about this problem. So how can we abstract even further away from the diagram? Well, we don't need to know anything about the houses. We don't need to know their size or their specific location, just that they're connected to other houses via paths. So we can essentially abstract these houses to these essentially labelled nodes, and we give each house a unique identifier, which is simply a letter of the alphabet. So the next abstraction allows us to represent the paths between the houses as a simple line, and that way we simply denote the fact that there's a connection between the two houses. But if we stop at that point, have we lost any information? Well, clearly we have, as each path has a length, which is expressed as its number of paving blocks. So we do need to keep that information. So we can attach a label, just as we've done with the nodes. We can attach a label to the links, which we call a weight, to each link in the network, and that's what we've done here. So once we're at that point, we can get rid of everything else. The clouds, the trees, even the houses themselves. They're all irrelevant once we have this abstract structure that we call a weighted network, which is basically a bunch of nodes connected by links.